Hi, everybody, and welcome. Thanks for joining us for the hidden story of PCB failures, lessons from the lab. I'm Michael Kuhl, Strategic Marketing Director with Element, and your host for today. While we wait for others to join, please let us know where you're dialing from. I'm joining you from gorgeous and sunny Colorado Springs, Colorado. I'm excited to say that today we'll uncover what really causes printed circuit boards to fail and how to prevent it. Whether you're in design, manufacturing, or in reliability and quality, you'll get practical insights that you can use right away for a variety of industries such as aerospace, defense, and consumer electronics. We're excited to have two knowledgeable experts today leading today's discussion. Russell Shepard, Technical Director of Electronics at Element Anaheim, with 40 years of experience in PCB design, manufacturing, and testing. We also have William Graver joining us, a master IPC trainer with 36 years in PCB and PCBA manufacturing, who has trained and certified professionals across the industry. Throughout the session, you'll see various polls pop up. Please take a moment to respond. Use the Q&A panel or the live chat anytime to submit questions, and we'll make sure we get to those as well. And we will try to get as many of those answered as we can throughout this particular webinar. Please follow us on LinkedIn at Element Aerospace and Energy, and subscribe to our Element YouTube channel for more exciting updates and technical content. You will also receive this recording via email afterwards, and also reminders to check us out on YouTube and to review this video there. To get us started, I'll hand things over to Russ to kick off the hidden story of PCB failures, lessons from the lab. Over to you, Russ.
Thank you, Michael. Hello, everyone. Welcome to the presentation. My name is Russ Shepard. I'm currently Technical Director of Electronics for Element Anaheim. Over 40 years in the industry, done everything from manufacture, inspection, quality, test. I'm also part of the IPC MIT trainers for the IPC A600 and IPC 6012, and I want to welcome you all. Thanks for coming. Bill?
Thank you. I'm Bill Graver. I have over 36 years experience in the PCB and the PCB manufacturing industry. I started in 1980 drilling holes in circuit boards. I'm currently an MIT Master IPC trainer in IPC 600, IPC 6012, IPC A610, IPC A620 training programs. I'm also a PCBA and a PCB subject matter expert. My main focus is our IPC training, and I've worked in the lab for the last 10 years. So I'm glad to be here, and I hope we can learn something from this presentation.
All right, thanks, Bill. A little bit about Element. We're the center of electronics and circuit board industries, the Element Anaheim and Baltimore locations. We have provided testing services for almost 50 years. Both labs are ISO 17025 accredited, as well as holding approvals from the DoD and many of the prime players in defense and aerospace sectors. In addition to testing, we offer numerous other services, such as training and certification, consulting, and expert witness. Bill?
Well, PCBs are the backbone of modern electronics. Their reliability directly affects system performance, safety, and longevity. Even a single undetected defect can cause costly failures, program delays, or safety risks, especially in mission-critical applications like defense, aerospace, medical devices, and electric vehicles. PCB failure analysis identifies these risks and can prevent future defects and, of course, catastrophic failures.
And during this, we're going to show a lot of common failures, but we can't cover everything that can happen to a circuit board. If you've been in the business long enough, like Bill and I have, you're going to see a lot of things. So what we're going to cover is some of the more common methods and common defects. Each failure analysis is unique, and each approach may be a little different.
Just when we think that we have seen it all, right, in our long careers in electronics, something always crops up that we haven't seen before. So, like Russell said, each individual thing is unique. So, what we're going to do is generally talk about these issues.
All right, let's get started. Our PCB failures, hopefully nothing like this happens to you, where you see flames coming from your equipment or your circuit board. If it does, put out the fire, and then we'll figure out how it happened. Okay, so we're going to understand failure modes in PCBs and how to prevent them. Our first poll. Let's see. We can launch this poll.
What do you think the probable cause would you say is the most common among PCB failures? Is it design, manufacturing, or human error?
Okay. Is everybody able to see the poll?
There we go, Russ. Yeah, we're getting submissions right now.
Okay.
Yeah, you would think, these are kind of unusual, Russell, that you mean probable cause could be design, right? Manufacturing, human error. You mean a human could make a mistake that would be the probable cause? Is that possible?
Yeah.
So
yeah, I know what my answer is.
I know
Yeah,
what
the
my answer
folks
is
in the
as
chat
well.
did just confirm that they did see the poll. But originally, I actually thought that folks were answering yes to all three in the chat. So I had a bit of a chuckle myself there. So.
Okay. All right. Let's see some of the results.
I'd be anxious to see what the results are. Wow. Look at that.
Yeah, it's kind of split.
Yeah. 35%, 35.7. Wow. So Russell, you want to let
whether
them
it's
off
in
the
design
hook?
or manufacturing, yeah, whether it's design or manufacturing, it's most usually human error. So if it's happening during those other processes, it's because of human error. 90 to 95% of all defects are because somebody did something. All right. Thank you, everyone, for that. Let's keep going. All right. Some of the failure modes we're going to talk about, some design issues, some manufacturing defects, some defects in the materials, the environment that the boards operate in, and then outside influence. And we're also going to talk about some methods of analysis, some visual inspection, electrical verification, and destructive physical analysis, or DPA. All right. First thing we're going to do is look at the board. We have a failure. Let's take a look at it. What does the failure look like? Is it external? Can you see it from the surface? Is it internal, buried underneath the surface? Does it show any kind of blisters or delamination? Are there any burned areas like you see in this photo here? Any contamination? Any type of defects in the solder joints? Or are the components themselves damaged? Bill, what do you think about that?
I think you made a good point when we were practicing this yesterday, that sometimes, like in this case, the burn sometimes covers up the defect. So of course we know this is a burn. We don't know at this particular moment how that happened, but I think it's important to know that, when we're looking at defects, especially visual verification, and we scan, let's say, an assembly or a PCB board, our eyes usually go to something that looks irregular. Again, this looks irregular, and our eyes will scan to the worst case scenario. This, of course, looks burned. Like you said yesterday, we have to be careful when we're analyzing this or dissecting this, that we don't, destroy the part that caused this issue. So,
Right, good point,
um,
Bill. And also if you see burning or some other material on the surface, that may not be the cause, that may be the effect. The defect
mm,
may be somewhere else on the board, and this is
right.
just the effect of that. Okay, so let's look at a few. So how we're going to approach a failure analysis. There's a couple ways to do it. If we're looking for some kind of electrical failure, we're going to try to find out where the defect is located. Is the defect a short? Can we find it between conductors? Is it between layers? Sometimes it could be solder bridging on a component or on a surface feature. If it's an open, is the open in a circuit trace? Is it a cut trace? Is it in a plated through hole in the barrel? Are there cracks? Are there internal separations? Is it in a solder joint? Are there cracks or cold solder joints? We're going to look at a few of those. So finding out what type of defect and tracing it down to the nearest point is going to help you immensely in trying to discover the root cause of that failure.
These things are going to stick out like a sore thumb on the surface. Internally, they may not show up on the surface, but externally they'll be on the surface and easy to spot.
Right. So when we're doing our visual, we're going to look for things like surface contamination, solder defects, any type of ESD, electrostatic discharge defect, or is there damage to the component? So we'll look at surface contamination. This could be anything from flux residue, handling defects, leftover process chemistry, corrosion, and other forms of contamination. So a lot of this, when we're talking about human error, a lot of this is handling defects. Just the way the board is touched. Are you wearing gloves? Are you racking them properly? When there's flux residues, how did it get there? Why is it still there? Is it a no clean flux? Any kind of corrosion could happen because of latent defects of the material being on there. It may happen down the road, not necessarily right away. If you see something like this picture on the right where you have flux residue, that can be cleaned off pretty easily, but if it's left there, that could cause corrosion on that metal surface, which could lead to electrochemical migration and shorting.
And one of the things there is going back to the human aspect of it, perhaps the human element here comes into play when maybe they were confused about whether this was a no clean flux and it wasn't cleaned, right? So, and of course now we have, either one of these boards, they're not going to be solderable. So, you can see that damage right there, but that's where the human element comes in. Could this been avoided? And most certainly, yes, could have been avoided.
Mm-hmm. Looking at assembly boards, looking at the solder joints specifically, are there cold solder joints? Are there cracks in the solder joints? Voids, for instance, in the BGA? Any type of solder bridging, like that middle photo right there. You can see two of those component leads are shorted together with the solder bridge. Or head and pillow, which has a lot to do with cold solder joints as well. That's the picture on the right. So any one of these can be seen visually. Sometimes you have to do some destructive analysis to find them. But what can happen, especially with like the head and pillow you see on the right, and sometimes these cracks are cold solder joints, the boards will function correctly at room conditions. But once the board or assembly has been in use and powered up, the board's going to heat up. These cold solder joints, these cracks then start to separate when you start to get the expansion from the heat, from the use, and then you start to get the failures. So a lot of times you're going to see failures when these boards are in operation, but then you bring them down to the bench to try to detect them, you may not be able to find them. So sometimes you may have to artificially heat up an area, maybe with a heat gun or placing the board in an oven, and then try to trace down the actual defect, because a lot of them don't appear until they are at operating temperatures.
In this case, these solder joints, it's very easy to see that they're a defect. The crack on the left, the solder bridging in the middle, and the head and pillow anomaly on the right. Russell's correct there that you're going to have a connection with that head and pillow, but in fact you're not going to have an adequate solder joint. So. Right.
So the reliability is of concern, even though the board is functional at room temperature. Oops. Okay. Okay, what's going on? Okay, next slide. Electrostatic discharge, or ESD. You can create component damage or circuit damage. A lot of these components are ESD sensitive. And again, human error handling these while not properly grounded, properly handling technique, things like that can create this ESD. When you touch a board, it's similar to kind of a static charge when you're touching a door handle. You walk across a carpet, you touch a door handle, you get a shock. Those electrical charges can be in the tens of thousands of volts. A lot of these boards are running at 3, 4, 5 volts. And you put that much voltage into some of these active components, and you're going to get some damage. And a lot of times you're not going to see damage as obviously as you do in these two photos. A lot of this, the damage from ESD is hidden inside these components. And these components that can be damaged are usually the active components. They're usually the QFPs or the BGAs. The other components on the board, like the resistors and the capacitors, they're passive components, so they would not be as ESD sensitive, but these active components are. And normally, the boards are going to be identified as ESD, but sometimes it's hard to tell.
Hey, Russ, we've got a couple really interesting questions in the chat. One, are these actual photos from the lab themselves? Are these actual ESD photos?
These photos are not from my lab. They are from some other studies that I've read about ESD damage.
Brilliant, brilliant. Another one is, can ESD damage be identified visually? Does it have any sort of special symptoms or things like that?
Well, in these pictures is visual, but a lot of times it's internal. And so they would have to be investigated like in an X-ray to see what kind of damage internally there was. I think what we can take away from here is we treat every assembly as ESD sensitive, unequivocally. So everyone who works on set assemblies, they have a ESD lab coat on. They're fully grounded to the table, to the desk, or if they're standing, wear wrist straps. It's very, very critical to this. And like sometimes in these pictures, hey, we can clearly define these things are burned up and really related to ESD. But many times we cannot see the damage unless a further investigation is happening. So our rule of thumb is we treat all assemblies as ESD sensitive.
Very cool. Thanks, Ken.
Okay. And then visually, some component damage that you might see. For instance, a cracked component, this resistor on the left, you can see this small crack here. Whoops. Somehow they keep advancing. I don't know if you're advancing it, Bill.
I am. I apologize. My screen's locked up, so I'm sorry.
Okay, we're on the component damage slide.
I got it.
Okay, we're looking at the cracked component, the resistor on the left there. And then this middle photo, you're looking at tombstoning. That can happen during assembly. It could happen post-assembly, where one side of the component has detached. And then you could get some overheated components, like the one on the right. You see the resistor there that's burned. That could be the effect of a short somewhere else, an overcurrent. It could be the wrong resistor that was placed in the board. Being that it's burned that much, it's hard to read the bands, the colored bands that are on it that will tell you what type of resistor it's supposed to be. So that could be an indication that something's happening somewhere else on that board that's putting too much current or more than that resistor can handle. Okay, we're going to look at a couple of defects that could happen to the board itself, the bare board, whether it's unassembled or after assembly, but to the board itself. We're going to look at conductor patterns, the laminate, surface finish, and some plated through holes. Okay. First thing we're going to look at is shorts and opens on the conductor. You can see in these photos here, this far left hand, you can see a short. That's where two conductors are connected, and they're not supposed to be. If these are uncommon conductors, that can be a problem. That can lead to a lot of defects. Number one, the board's not going to work correctly, but you could get some arcing and some overheating because of that. The next photo over here, that's of a cut trace. So there you have an open. So it might not be as obvious as that, but it gives you an idea of what an open trace may look like. This middle photo here, we got a little bit of misregistration and some bridging of the conductor to the nearest land. And that's going to cause shorting. That could happen for a number of reasons, but could be because the hole is misaligned and out of registration to that nearest conductor, or it could be an under etch condition of the bare board. And then on the right here, you see some cut traces and some lifted conductors. The conductors can lift anywhere if there's not a good bond to the base substrate. If there's not a good lamination bond, and you have conductors lifting, maybe not this dramatically, you're going to create opens, and you're also going to create shorting hazards as well, which could create burning or overcurrents.
We had another quick question in the chat, particularly for PCB panels. Is there a concern if the panel is too porous?
Too porous?
Yeah.
It's possible if the material is very hygroscopic, or if the board is going to go into a very high humidity environment. And many times, if that's a known instance, there'll be precautions like conformal coating applied to help seal the board in. But as far as being porous, not really. There's an overcoat, like a butter coat of epoxy, and then there's usually solder mask, and then on the final assemblies, like I mentioned, there could be a conformal coat.
Usually,
Cool.
the foil that is used, or the material that's used, is spec'd. For example, IPC 4101. So the material is spec'd to match the type of assembly or the type of circuit board that's required. So then when they do surface preparation, and they actually scrub the board and put an image on there and plate that image up, it really everything porous, it would not apply in this situation because it would be taken care of by the material that's called out on the drawing. So I've never heard of a porous issue on foil. So it's highly regulated.
Very cool. Thank you.
All right. Laminate. The base laminate itself, you could see blisters or delamination. I did notice there's a comment in the Q&A about that. So here we are, Fred. We are getting some delamination. Could happen from moisture entrapment. It could happen from any kind of contamination on the surface prior to lamination. And this could happen during manufacturing, or this could happen after the board's been in service for a while. If you're in a high temperature, high humidity environment, this is going through any kind of thermal cycling while it's in an environment, this could happen. And the defect can create opens and shorts, and that's where we're going to look to see if there's any lifting of the conductors away from the plated holes, and also if there's any conductors that may be in contact with others. You can see on that picture on the left right here that delamination goes right to that mounting hole. If that mounting hole is mounted to a ground or chassis ground, and you've got conductive material right next to that, you're going to get migration to that, and you're going to get a ground short. And then that whole board is going to stop working, or at least that portion of the board is going to stop working. The other thing is the board can start to just separate, come apart, and you could have adjacent parts. Again, with the chassis, it could be grounding to that, but you're going to get a lot of interesting things happening if you start to see this delamination. And a lot of it may not be this exaggerated like these photos. I use these for to demonstrate what it is. It could be very small delaminations happening between conductors as well. And what you're doing is you're opening up that material, that base material now, and now there's a path, and you can get path for electromigration, shorting, arcing, things like that.
In any kind of separation like that, you're going to have issues with moisture having the ability to creep in. And, you know, a little tiny blister, a little tiny delamination can migrate larger when stress is applied. And in case of the delamination, the board can actually, and I've seen instances where the board started out with a little tiny delamination and got larger and larger and larger, where you could actually take your fingernails and pull the board apart. So these things are, and most of these things happen in the laminating press. They begin in the laminating press. And so these, of course, in these cases, even the smallest blister delamination should be investigated.
All right, now we're going to get to the surface finish here. Photo on the left, we're looking at some de-wetting or non-wetting. That's where the solder isn't sticking correctly. This could affect the attachment of the lead to the land, and you could get cold solder joints. You could get separations, things like that. And then the picture on the right, a little bit of non-wetting, possibly some oxidation there. That's going to affect if you're doing any kind of probe work or soldering to those lands.
Yeah, they're highly unsolderable. Those the figure on the right.
Right. All right. And then plated through holes. We're looking for voids, misregistration. We saw a picture of misregistration earlier. This little diagram is showing some voiding in these holes that can create opens. You can see the ring void here in this one. A lot of times when it's soldered, you can't see these until we do some destructive analysis, which we're going to talk about here in a minute. Now, we're going to talk about some of the failures that can happen during the manufacturing of the board itself. We're going to talk about some drilling, plating defects, registration, and the material. First of all, we're going to talk about some drilling defects in the plated through hole. That can create some rough hole walls, which could lead to wicking and plating folds like you see on this right-hand photo. You see these folds here from the hole formation process was very aggressive, And now we have some points here that are not completely plated, have some cracking, some folding of the copper. Now, again, this could pass the initial electrical test while it's at room conditions, but once it gets into the field, operating temperatures, that board is going to expand, and these cracks and folds will also expand. And then over here on the left, we're looking at some interlayer separation. This could be caused from the drilling, and my reasoning for that is you can see the flaring of the internal layer here. They call that nail heading. And so the drilling process, as it's drilling through this material, these drills over here, like you see on this left-hand photo, they're going very fast and they're very high. These boards are made out of epoxy. And when that drill goes through that epoxy, it could smear, melt and smear that resin and drag it over the surface. And it's going to be very hard during your hole clean to try to get that out of there. So these defects can be built into the board, even though they're passing the initial test because of they're at the normal room conditions. As this progresses into the operating temperatures, again, that could affect these electrical connections.
Yeah, so there's not going to be a connect. It's possible without that smear being removed that you're not going to have a connection from an inner layer to the plating. The plating may look great, could look great, but because the smear or the resin that was smeared onto the inner layer was not removed, you'll have plating, enough plating, but you won't have a connection internally. Thus, it's going to read and open.
Mm-hmm.
Another great question from chat along this line. Is PTH roughness a root cause for voids?
It is an indicator. It's a process indicator that there's something going on in the hole formation process. So if the drilling isn't smooth and clean, yes, you can create these types of anomalies, which could they could turn into defects. Not necessarily, but they have a high probability to jeopardize the reliability of the product.
Like, right, if you look on the screen and that left drill, that's a drill machine, and that's the exact one I use. Let me rephrase. That's what I broke my teeth on in the industry. So in the formation of a hole wall, there is each drill bit has a drill life. Let's say it has 1,000 hits, for example. And let's say for whatever reason, the drill bit extends beyond that, it begins to dull. And that can rough up the hole. And also as the drill goes down into the hole, they have a feed rate and then a speed rate. So they have a feed rate, how quickly it goes down to the hole, the bottom of the hole, and how it comes up. And of course that affects the speed. So if the drill bit is dull, if the feeds and speeds are not correct, and if the entry material is not used or is not correct, you're going to have really rough hole walls. So there's a lot of factors involved with smooth and opposed to rough holes.
Very cool. Thank you so much.
Mm-hmm. All right, some other plating defects could happen during the plating process. So we're looking at thin copper, copper plating voids, cracks in the plating, and then interlayer separation of the internal layer to the plated through hole copper plating. So a lot of these defects in the plating can happen during the manufacturing process. Cracks, possibly during some thermal excursion, whether that's reflow or if you're doing the Hassel operation. Same with the separation. If you don't have a good bond to that internal layer, you're going to create a discontinuity. The plating voids themselves can happen any number of ways. We talked about the folds. We could talk about the activation of the drilled hole not getting down into some of these high aspect ratio holes. And so you see here, this photo on the left, you have what's called a ring void or a circumferential void. That's going to keep the electrical current from flowing from this layer to this layer if that's needed.
They have a barrel crack in the middle. And Russell, would you say that's that separation there? You think that could have been caused by the smear process, a poor smear process?
Yeah. It could be caused from smear. It could be caused from the whole activation, the electrolysis line, not getting a good bond. Maybe the internal foil wasn't cleaned well enough for that plating to bond to that.
Yeah.
So any number of reasons. It could be a thermal, mechanical, or a plating defect. Okay. Then we're going to look into the material again, and we're going to look at delamination. We looked at it from the surface. This is in the cross-sectional view. You can see this here. We're getting a separation of layers, and that could happen during the manufacturing process. And this is something that you might not be able to see from the external view. It may only be visible if you do a destructive analysis like this. And then over here on the right, you're looking at some wicking or some electrochemical migration. That can happen when you have plating solution behind the hole wall, and then you have an opportunity, whether it's through a delamination or a crack or some resin starvation, where the copper plating will actually start to migrate. And as it migrates, it's going to go towards an uncommon conductor. And you've already reduced dielectric here, so you could be getting some issues there. Or if it keeps growing, you could actually short that out.
Very important part of this is, you know, electrical spacing is very, very important. And one of the problems with what Russell just talked about was the fact that we're going to violate electrical clearance. So.
Okay, so we have another poll here. What is the -- enemy of circuit boards? Is it heat, moisture, or electrostatic discharge?
Very interesting.
All of those are bad.
The one's the worst, right? What's the number one enemy of circuit boards?
Right.
Gentlemen, while we're waiting on responses to come in, we've got a really good question as well in the chat. Folks are wondering what can be done from board users to detect or prevent before it becomes a problem.
Can you read that again?
So what can be done from the perspective of a board user or an end user to detect a problem or defect before it becomes a problem?
Well, I think a lot of it is testing. You want to get as much information in each step of the process as possible. So you want to do in-process checks. If you're the bare board manufacturer, you want to make sure that you're getting enough copper plating, the lamination process before it gets to the next step. Because if you're just pushing boards through the process with defects, all you're going to do is throw the board away at the end. So between the bare board level and the assembly level, that's where you want to do a lot of checks. You want to do some conformance checks, cross-sectioning, visual, electrical testing. You want to make sure as much as possible that board is not going to fail prior to assembly. Because once you start putting components on it, there is a lot of money in those components and a lot of process steps. And once that happens, it's game over. If that defect is built into the board before assembly, then you're done before you even get started.
And Russell makes a very good point, because in process. So if you catch something in process, this should be part of the quality program. Testing in process is vital to building good boards. It's not a hindrance. You say, well, it's going to slow us down. Well, as Russell made a really good point, if you catch it with the first board or the second board, you're not going to plate up 100 boards or 1,000 boards. So in-process quality control checks, testing, AKA testing, is vital to making a quality product. You say, well, it's going to cost me a lot of money. Well, it's going to cost a lot of money, more money, to test something after the fact. So in-process testing is very vital to building good quality product.
Thank you so much.
All right, let's see the results. Yeah, all good answers.
Yes.
And they are all bad. But we did check. We asked the almighty Google, and they said that electrostatic discharge was the #1 enemy to circuit boards.
Yeah.
Now, these are assembled boards, but yes, that is the #1 enemy. But I would say all three are bad.
Yeah, and the key thing there is, with regards to ESD, it's 100% preventable, right? If we treat every
Correct.
assembly like it's ESD sensitive, that figure goes way down, right? So sometimes we have very little control over moisture or heat, but certainly ESD, we can control that.
Okay. Thanks, Bill. All right, we're going to look at some equipment here, some visual, some DPA, and some forensic equipment. So for the DPA, it's mainly cross-sectioning. So you're going to need some cutting tools, some sanding, grinding tools, and polishing. What you're seeing here, this is usually for some high-volume microsectioning, some conformance-type microsectioning. If you're doing cross-section DPA for a failure analysis, you're going to want to take a more laborious approach, where you're going to want to identify where it is. And sometimes it's going to take time to sand down to a certain location, especially if you're looking for a short or a calf failure, things like that. Visual, these are pretty common. Most board shops, assembly shops have these already. Optical comparator, microscope, and a coordinate measurement machine or other type of dimensional analysis if you're looking for circuit spacing, width requirements, annular ring, and so on. So forensic equipment, this is where it can get a little costly. You're looking at X-ray, scanning electron microscopy, which is SEM, TMA, it's thermal mechanical, DSC if you're looking for cure factor of the material, and then IC is ion chromatography if you're looking to identify any type of surface contaminants.
Now that picture on the right there, Russell, is, before we talked about a head and pillow, there's a really good SEM image of a head and pillow anomaly. You can see where you have that black line, that's your separation there. So for all practical purposes, there is no connection there. And
Right.
we were able to spot that in the SEM.
Mm-hmm. And then reporting. That's the most important, right? You want to define the problem, you want to collect the data, create a failure timeline, and then you want to select the useful data in your report. So going back to the beginning of this presentation, we were looking at how or what are we looking for. We want to document that. You want to use photos, you want to use electrical measurements, you want to record all of that, even the timeline of how it got to the failure. The board was in use for X amount of hours. It was at this temperature and this humidity condition. This voltage was applied to it. You use that in your factoring of how that defect happened. Even if it has very little to do with the actual failure, at least you have it documented and you can go back. So when there's questions asked, you can present that data, especially being in a lab environment like we are. This is our bread and butter. We want to show the customer when we're looking for a failure, we're documenting everything. We're not just going to cut the board up and say, well, we didn't find anything. This is what we did. And a lot of times you may not find it, because a lot of times the very first thing that goes is what caused the failure, especially when you get burns.
And I think one of the key things here, Russell, is sometimes we're tasked with finding an issue, right, that's clearly defined by the customer. But while we're trying to find that issue, we find other issues, right? And of course,
Right.
we report that as well. So that's the value added service that Element in our labs can offer. So, if we're, checking on voiding, for example, and we see a crack, they say, well, we need to know what the percentage of voiding is here. And on our way to check the voiding, for example, we find cracks. That's useful information and data for our customers. And that happens almost every single job that we do. We find other things. We're tasked with a certain process or a certain SOW, but then on our way, we find other useful data that's helpful to our customers.
Mm-hmm. Okay. And then some limitations, cost, experience, and of course, the all-important time. So some of this equipment and materials can be very cost prohibitive. For instance, the X-ray and the SEM are can be very, very expensive. You're talking hundreds of thousands of dollars. And then we get to experience. This is where I think it's the most important, I think. How to approach the failure is going to take time, and it's going to take experience. How do I approach it? Again, we see a burn on a board. Well, we don't just say it's burned. We got to figure out how we're going to approach it. So that experience is knowing how and what to look for and what approach will be taken.
Yeah, and that is one of Element's greatest assets, is the experience. We've seen this before, or something similar to this before, and we know how to, and we know what to look for. We know how to find the anomaly, find the issue, and what to look for, and then, most of the time we can offer solutions as how this can be prevented in the future.
Mm-hmm. And Bill, you have a saying on a dollar spent?
Okay, my favorite saying, here it is. Ready, everyone? For every dollar you spend in testing, you're going to save $100 in defects and anomalies. So for every $1 you spend in testing, you're going to save $100. Now, so you figure there's a $99 difference between those. And that is quantifiable, and it's I think it's important to know. So because Russell was talking about cost. Well, these things might be costly. However, you're paying for years and years of experience. You're paying for equipment that we already have, and we know what we're doing. And so you say, well, $1 spent saves $100. I would go for that any day of the week. I don't know about you, Russell. Costs are important to me. I live on a budget, and so I think that's vital.
Yeah, absolutely. It's like maintaining your car. You either pay them now or pay them later. And the most important, I think, is time. A lot of these products are out in the field, whether it's a soldier in battle, if somebody's in an airplane, there's a satellite, there's medical equipment. Time is money. Time is somebody's life. So if this is something that can be done right away, then that's very important. You don't want to waste time. And when you're starting to see defects, to not address them. And that way you can catch them before they go out. But if there is something already in the field that's defective, you need to find out how and why so they can be fixed or recalled. And in summary, failure analysis, what it's worth, understanding the failure modes. You want to prevent future failures. What's the liability of these failures? And of course, the costs. All right. So we want to open it up for Q&A.
Yep, the floor is open for Q&A. We've got a nice solid 10 minutes. Perfect timing, gentlemen. to answer any and all questions for PCBs. We've got a couple already that we can kind of go through. So the first one, do you commonly see voids in solder joints causing PCBA failures?
Yes.
So a void is a symptom for sure.
That was quick.
Yeah.
Well, voids are a problem. So whether it's a small void or a small percentage of voids, for example, BGAs have an IPC 610 says BGAs can, they're tapped out at 30%. That's a problem. So voiding can be a problem when it's minuscule, and when when we have large voids. Don't forget, when we get an assembly, that assembly has a shelf life, and most assemblies have they're gonna have stress. So think of a void as a small little kind of air bubble in the assembly, and it's possible that those voids can migrate into cracks. It's possible. So yes, is there a problem with voids? Minor voids may not be as problematic as very, very large voids.
All right, another one. Let's see. What issues happen with stacked VIAS?
So that's stacked vias.
Thank you. Marketing guys, come on. be nice.
So there's a few things that can happen with stacked vias. The number one issue with stacked vias, in my opinion, is the target land connection. So as you stack these, you have to make sure that each via is connected to the one below it. I've seen stacked vias 10 high, and when you get into that much of a arrangement, you're bound to see something, and usually it's the target land connection. Also with stacked vias, you can get some registration issues where you're going to get your target land annular ring, which is going to reduce your contact dimension. You're going to get sometimes you're going to get some penetration of the target land. So stacked vias are very important to high density boards, but they can also create a lot of problems. And there's ways to detect those problems, whether it's through testing, decoupon type testing. You can always cross section a board to death, but you're never going to see everything. So it's very important in the processing, the manufacturing of those stacked vias, that you get the registration and the target lands contact dimensions correct.
And there's a lot of debate in our industry right now with regards to stacked vias, staggered stacked vias, and so there's a lot of work being done in our industry in talking about that. And so stay tuned for some other. Russell and I could talk about this for hours. We don't have that much time, but suffice to say, it is an issue in our industry. And Russell's correct. In IPC 600, for example, they make a point talking about micro via the target land. And so, for example, for class 1 and 2, we allow a little breakout. For class 3, we allow no breakout. So that connection right there is vital to the any micro via processing.
Outstanding. Another question. Could a no clean flux create corrosion? That's a good one.
Okay. I'm on a crusade.
All right.
I'm on a crusade.
We hit the controversy. Thank you.
All flux should be clean. And okay. I'll answer it quickly. Yes. Right? Without going into too much detail to help you, it is my opinion. I've been doing this for close to 40 years. I believe all flux, even cleanable flux, should be cleaned. That's my position. So I don't want to be controversial here, but
That's
there
why
is
that's the price of admission right there, Jeff.
Well, let me just say this. With all quality, here's where my stance are. With IPC, for example, Russell can verify this. We talk about minimum and maximum requirements. In my opinion, if we want to build good quality work, we should. You're right. We say, well, okay, this is the least we can do. My question is, why not do better than the minimum requirements? Why not do better, right? And so being better is cleaning everything. That way you eliminate that problem with corrosion. And yes, I have seen assemblies that have said they were no clean flux and there was corrosion. I have seen that with my own eyes, and I've probably inspected thousands of boards in my career. So yes, I have seen it. But it's a big controversy.
All right, we have time for just one more question. I got it right here in front of me. Is there a possibility? So the question is, how about using IST coupons to simulate the quality of the PCB?
Ooh.
So there's a number of different ways to simulate the reliability. That's one. IST coupons are a way to thermal cycle the boards using current. So it's called current-induced thermal cycling. And that is one way. There are other ways, such as the D coupon test. The new Appendix A D coupon can be run through a reflow simulation while monitoring the resistance. And you can use different peak temperatures, and you can also use any number of cycles. Typically, the minimum is 6. But what you're trying to do is you're trying to exercise those microvias. There's other ways, if you don't have microvias, if you don't have IST type coupons, you can simply do thermal stress and cross-section. You can do thermal cycling, but anything that simulates the end-use environment or that's going to exercise those parts is going to be a good reliability check.
Yeah.
All right, thanks so much, gents. I believe we have one more poll question for everybody, if you want to switch over to that real quick.
Okay. Final question. Would you like a member from our team to reach out to you for further discussion? That's a yes, no, or send a follow-up email for now.
Well, while we're waiting for that poll question, I actually have a question, or a question directed towards me, which is very unusual, and I appreciate it. This is actually kind of cool. So first of all, a great comment from the audience, great webinar. Will more of these webinars be done in the future? You better believe it. We have been really pushing a lot of these kind of sit downs with our experts within Element, and of course our guest speakers as well to help us out. Usually we schedule these about 1 to 2 a quarter, and that number is going up in the next year. So there's plenty of opportunities to sit down with our testing experts, as well as our application experts. So I think we can go ahead and start kind of closing this particular session out. So first of all, thanks so much, Russell and William, and thank you to everyone, especially who joined us today. The engagement has been really off the charts. So I'm kind of blown away with the kind of amazingness of this audience. We hope you found this session valuable and took away a few insights you can put into practice in your own PCB design, manufacturing, or reliability programs. If you'd like to learn more, request a quote, or connect directly with our experts, you can reach us anytime at element.com/contact us. And don't forget, you can subscribe to Element's updates for upcoming webinars, as I said earlier, technical insights and industry news at element.com/news. We appreciate you for spending time with us today, and we look forward to seeing you at our next session. All audience members and everybody who registered for this webinar will receive a copy by email here in the next day or so, as well as, of course, this will be posted to YouTube for your team's review or your your own SMEs review here in the next 24 hours as well. So have a great day, everyone, and thanks again for being a part of the hidden story of PCB failures, Lessons from the Lab. Thank you so much.
Thanks, everyone.
Thank you.